Hi, everyone. My name is Laura Line, and I'm pleased to welcome you to the National Academies of Sciences, Engineering, and Medicine, and to our monthly webinar series, Climate Conversations, Pathways to Action. Our conversation today will be recorded and available to view right here after the event. If you would like to ask questions, please submit them in the Slido box below the video at any time, and we'll incorporate them into the Q&A section of our programming. We also encourage you to participate in the polls that will appear in the same location and give your feedback after the event in the survey linked above the video. As a reminder, the views expressed in each conversation are those of the participants and do not necessarily represent the National Academies. For today's climate conversation, reducing and removing methane emissions, we'll be building on our February 2023 climate conversation on methane, which is linked on the event page. To kick us off, I'm thrilled to introduce my colleague, Brent Hurd, Senior Program Officer with the Board on Energy and Environmental Systems and Co-Director of the National Academy's study, Atmospheric Methane Removal, Development of a Research Agenda.
Thanks so much, Laura. Before diving into the conversation today, I'd like to take a brief moment to share some background on recent National Academy's work addressing methane. Last year, we released the consensus study, A Research Agenda Toward Atmospheric Methane Removal, chaired by today's moderator, Gabrielle Dreyfus, and with committee membership from one of our speakers, Hinsby Cadillo-Quiroz. That study addressed the need for developing approaches for atmospheric methane removal, providing a two-phased research agenda for this topic area. This committee recommended advancing some priority research areas in developing atmospheric methane removal approaches within 3 to 5 years. Then, with the results from the recommended research, having a second phase assessment, which would be able to more robustly evaluate the technical, economic, and broader social viability of methane removal and its potential for climate scale impacts. But importantly, a key conclusion of the report is that atmospheric methane removal technologies, even if successfully developed, will not replace mitigation on timescales relevant to limit peak warming this century. So it's important that we talk about both removals and mitigation in conversations like the ones we're having today. The National Academies has addressed accounting for and reducing methane emissions in our work involving life cycle assessment methods and applications, with our speaker Deborah Gordon having contributed to those efforts. If you're interested in learning more, I encourage you to explore the links on this event webpage. But without further ado, I'm pleased to introduce the moderator for today's conversation on reducing and removing methane emissions. Gabrielle Dreyfus is a chief scientist at the Institute of Governance and Sustainable Development, working at the interface of science and policy to advance knowledge and action to slow warming in the near and long term. She chaired the National Academy's Committee on Atmospheric Methane Removal and is an adjunct professor at Georgetown University. Gabrielle, now over to you.
Thanks, Brent. Thanks for organizing this climate conversation on methane mitigation and removal. I'm very pleased to bring to you today two excellent panel speakers for this topic. First, we have Deborah Gordon, who is a senior principal at RMI and a methane emissions expert who began her career as a chemical engineer in the oil and gas industry and has worked in the public and nonprofit sectors as an energy and climate policy analyst. In addition to leading RMI's Oil and Gas Climate Initiative, she serves as a senior fellow at the Watson Institute of International and Public Affairs at Brown University. We also have with us Hinsby Cadillo-Quiroz, who is an associate professor at Arizona State University with a dual appointment in the School of Life Sciences and Biodesign Institute and leads the Ecology of Microorganisms and Ecosystems Laboratory. His current research focuses on methane production, consumption, and possible management questions, including microbial interaction tests with pure cultures, small to medium-scale bioreactors, as well as environmental studies of landfills, northern forests, and tropical peatlands in the Amazon basin. So welcome to you both. We are going to start with a general introduction to the methane topic by diving into the more personal relationship of what is methane? Why is methane important to you? And let's start with you, Debbie.
Thanks so much, Gabby. My journey here has been very long. It started with the oil crisis of the 1970s, which got me very interested in energy and hence into chemical engineering. And then during my first job as a chemical engineer for Chevron, one of my assignments was to take soapy water and go out into the oil field and find gas leaks. Now, at the time, it was just thought of as a waste. I mean, these were oil operations. And it was actually, interestingly, I was only there looking for methane from an environmental point of view as a possible, at the time, kind of somewhat neglected input to air quality, because it was really considered to be non-methane organic compounds that created smog, which we know now is today is not true. But I have to say, it was one of the projects I probably failed on, because there were leaks everywhere. They were small little bubbles everywhere, and it was really hard to figure out how to stop them. At the time, it was considered a nuisance, and it wasn't large enough to be a safety concern. And now we know, which we're going to talk about today, all the reasons why we should be managing that methane.
All right. So early detection techniques. Over to you, Hinsby. What brings you to the methane topic?
Well, thank you. So I discovered methane as a byproduct when trying to understand when the liquid world and the soil world meet each other, and this is wetlands, right? So it's the encounter of two forces where the chemistry, the physics, and the biology suddenly produce a really important product, which was the bubbling methane out of a wetland, for instance, right? So that moment, I didn't realize of the complexity of that relationship. But more importantly, in the last years, how that complex relationships actually transform of many functions that leads to how trees grow, how certain more successful micro animals or medium-sized animals develop, etc. And suddenly you get lost on the complexity of chemical, biological, and ecological methane functions and more. And the point to remind everyone that I feel very passionate about it is that methane functions are very controlled by microorganisms, by methanogenic archaea, methanotrophic archaea, and not frequently we harness their power in a natural environment context. And here I am now thinking on things at the micro scale, how can they work at the kilometer scale? So nice journey that I had.
That is a nice span of scales there. So you've touched on this both in your introductions, but Debbie, can you tell us a little bit more, just ground us in some of the basics? What are the main sources of human-related methane emissions?
Yeah, so the easiest statistic to remember is a third, a third, a third. And I'm going to explain the nuances of it. But just if you can remember that, you'll have a good grasp of this. A third energy, methane from human sources comes from energy, about a third comes from agriculture, and about a third comes from waste. That differs a lot around the world. I mean, India has a lot more cows than, another small country might. China has a lot more coal. US has a lot more oil and gas. But the energy part is oil, gas, and coal. And the agriculture part is rice and animal feedlots. And the waste part is solid waste and water waste.
And Hinsby, can you help put us in context? So we've got these human sources of emissions, but you also talked about microbes. So microbes span, you talked about humans harnessing microbes. Help us put into context the human emissions with the natural sources.
So natural sources, it has a third, right? We're comparing the third that Debbie pointed. However, it's a third that comes from the largest area, while the agricultural and industrial ones are very focused, very concentrated. This one now has like thousands of square miles, etc. And thus, it's like a large variation, because you can have from coastline wetlands, you can have the flooded forest in the middle of the Amazon, you could have even desert environments after a rain event can actually be an important methane source. So as we humans start interfering, colonizing, using lands in many different forms, we start changing that balance, right? And as conditions, the surrounding conditions start changing, then the emissions also start taking new directions that we are now recording, that we're now living and witnessing. So, yeah.
So we know, but we're relating this in the kind of greenhouse gas climate space. We know that carbon dioxide emissions or carbon dioxide concentrations in the atmosphere have continued to increase, largely as a result of burning fossil fuels. What's the trend for methane over, say, over the past 10 years? What are we seeing, and how much of that is directly attributable to human activity? Debbie?
Yeah, so like CO2, methane emissions have only gone up. And I think Hinsby will speak more to it even as to why. But what was very concerning was a couple of years ago, we saw the largest ever increases. So now we're at even higher baselines where we're increasing continually from. And what makes methane so important is just how warming it is. So I always think about it in terms of blankets around the earth, that if you have one blanket, which is CO2, and that blanket's going to stay on you for hundreds and hundreds of years. You have these other, almost like when you're sleeping at night, you're pulling on and off the covers. You have these shorter actors, methane is one of them, but it's like 80 or more blankets over the short term on you that that are coming and going because it's a short-lived climate pollutant, but it's very amplifying at the rate at which we are warming the planet.
Yeah, I think Durward Zelke from my institute is quoted as comparing, CO2 might be bringing the planet to a slow boil. Methane is the blowtorch being brought up to the planet. And Hinsby, as Debbie was alluding to, there was a fairly noticeable spike increase in methane concentrations over the last 3 or 4 years. Can you tell us a little bit more about what we understand about that trend?
Absolutely. Thank you. Well, to the point, right? Like methane does not behave too linear. If you think about the microbial process, it's actually and it tends to have this growth that are explosive. Now, if we think about some of these environments, some of these regions that have been having different conditions, but then let's pick the permafrost, or let's pick the tropical wetlands, for instance. As the conditions have started changing, this non-linearity, this response, this feedback has been expressing, and that's likely one of the reasons that have been attributed to the spikes that we've been observing. Some of the spikes of like 2022 are literally record-breaking spikes, right? And the best explanation, the best attribution, which is still limited, still need more work, but the best attribution shows that this is coming from these places that have lots of carbon, because naturally have been storing it and cycling it in slow rates. But with the new feedbacks, those are transforming at a faster rate. And we definitely need to quantify them better, but we do need to keep them as a tracking point to understand these large changes that are happening in the increasing methane in the atmosphere.
Excellent. So I think we're going to move now into a deeper dive, but just to pick up on a few of these points, Debbie, this idea of methane as the natural gas component from the oil and gas sectors kind of being a waste product, and the legacy of that as we're still seeing very significant leakage, and Hinsby, this idea of the microbes really being a major control, and this idea of nonlinearity and feedbacks being so important. And just I think the global carbon projects, they just the updated global methane losing a word, but the updated inventory of methane sources, I think just came out a few months ago, and they created a new category for this iteration on essentially indirect human emissions because of the changes that we're seeing in reservoirs, but also other some of those feedbacks that you're talking about, Hinsby. So as we dive deeper, let's talk about, Debbie, going back to some of those anthropogenic sources, going around with your bubbles and what's happening with the leaks. Like what can we realistically, what do we have for mitigation? And can you tell us a little bit more? We know there's technical potentials that we talk about, but what are the barriers to achieve them? Like what is realistic in the mitigation space?
Yeah, so just to backtrack a little bit to the Glasgow COP, the Global Methane Pledge was signed on to by most of the nations around the world. I think it might be up to about 160 or 165 nations now have signed on. Those nations pledged to reduce methane, each in their own sources, by 30%. That's, again, like everything in this space, is not necessarily easy to say it should be reduced that much everywhere. We really think that the oil and gas space can reduce methane 75%. And in fact, if everyone produced their oil and gas with as little methane as the best methane producer, one of the best is Norway, we would probably reduce that 90%. So there really is a huge opportunity here to achieve. And the benefit from the oil and gas side, this is not true of the other sectors, is that methane is a commodity.
Mm-hmm.
Once upon a time was a waste. Gabby and I were laughing before because my bio said that I was from the oil industry, but it's clearly the oil and gas industry now. Back in the 70s, it was the oil industry. And in the news today was even discussions of what is happening in Iran how it's going to change gas markets and gas prices. And so this commodity of methane, which is natural gas, natural gas is made up about 90% on average of methane with other things in it, which we'll talk about later. But the idea of it being a commodity is something that really gives the oil and gas sector that ability to act quicker and faster and better than, say, waste or agriculture, where it truly is a waste. And now you're talking about regulation. So you're going to need a lot of regulation in most of the sectors. You'll need some regulation, and the Global Methane Pledge helps. Certainly, there are other things I can talk about going on within the industry to pledge lower methane. Again, trying to best each other. It's very competitive. But this idea of the thing that hampers the commodity control of methane from oil and gas is the fluctuation of prices. Because if it's worth a lot, you want to keep it in the pipe and sell it. And if it's not worth so much, you'll dispose of it. You're not going to invest a lot to stop it from leaking. And so the fact that the oil and gas sector has such fluctuation and volatility in its prices makes it very challenging, I think, for this industry. And then you have issues like you have countries that are harder to manage, like Russia is a good example. It's very hard to bring them into this space and really hold them to bear. Then you have a lot of remote locations. A lot of oil and gas is in the middle of nowhere. And so monitoring it, or offshore where you have very harsh conditions like wind, so it's very hard to maintain. There's just a lot of nuances in this industry, but again, there's the opportunity to act here. And we know that there's huge differentiation in how these different actors, countries, national oil companies, international oil companies, how they manage their resources. And if they were all doing it as best they could, we could see this 90% reduction.
And just to pick up on that one more point further, Debbie, we talked about, the blankets. If we were able to get that 90% reduction in the oil and gas sector, or the 30% reduction that the Global Methane Pledge is working towards, what is the kind of climate impact we'd be talking about?
Yeah, this is great. It's something you, Gabby, and I have written about recently, and it's very eye-opening that together with CO2 mitigation, if we really task ourselves reducing methane and CO2 together, we could be below 2 degrees C. I mean, we're reaching 1.5. And we're headed to over 2 or 3 or 4. And the idea of actually making progress on methane immediately and CO2 significantly over the course of time with everything we need to do there is really, it will protect us.
In Hinsby, on the oil and gas, it seems like those are non-technical barriers, right? Like their technology is there. We've got satellites and other things. We're starting to see the leaks more clearly. You mentioned about some of these microbial systems and how much more spread out they are. And you do work in landfills and in other systems. What are the prospects and what are the challenges around managing methane from those systems?
Yes, so there are actually quite a variety of challenges. So although I would say, like, in terms of opportunities, in terms of magnitudes, it's a very large and also can be combined with co-benefits of other approaches. At the same time, there is still a significant level of technical knowledge missing. And I'd like to maybe explain in a few examples, right? One example would be the idea that forest, for instance, forest management, reforestation efforts, etc., has been primarily considered through a lens of carbon, CO2 removal, etc. But microbes that consume methane, they do exist, they do live, and they do have measurable activity in tree stems, in leaves, for instance, right? And if we take the 1 trillion trees that exist right now, and the ideal of reforesting another 1 trillion or half a trillion trees, that amount in terms of area, surface area, is a large universe, large exchange surface for removing a very difficult, very difficult task, which is diluted methane at atmospheric levels, right? But do we even know how those methanotropes that could live on those surfaces, how can they be successful? Which ones are they? How do they solve their energetic needs when consuming something that is very diluted, right? So that's, for instance, something as a fundamental microbial knowledge that has been missing because we did not consider that possibility. Another option is related to management of lands, for instance. In the annual budget, in the methane, global methane budget, you talk about the indirect emissions category. And one that is so easy to miss, but at the same time is so powerful, is the mining. Okay, so mining, for instance, of gold, which actually has a high value to extract right now, the market is very high. Regardless of which approach you use it will change the landscape, it will change the topsoil, it will change the natural function that ecosystem had it. And it will not change it in 100 meters. It will not change it just in 1 kilometer. It will change it in thousands of kilometers. These are like large mining operations or large areas sometimes required to concentrate enough gold, right? Well, when you do that, you blow the capacity to remove atmospheric methane of those ecosystems. Not only that, is that a common observation for the tropical regions is that you are left with depressions, with holes, that the rain come and beautifully fill that with water. And water and carbon that can fall from any surrounding area means methane. So that's a whole new emission in a place where you used to have consumption, where you used to have removal, right? So that's an indirect. And now what do we do? Like, how do we recover that place into something reasonably removing, right? Well, the capacity of the soil, the combination of the microbes have been completely changed in so many ways now that it needs to be re-understood, and graciously can also give us that opportunity to channel it to perhaps maximize that function of removal, to bring it back at a higher capacity. But we don't know how to do it. We don't have the technical data. We don't know the microbiological data, the ecosystem data, etc. And it's so important to get into solving some of those technical. And if you solve that, by the way, you could also combine that with an economical value proposition, along with the not just benefiting for the removal of methane, but also, as I was saying, in reforestation efforts with the CO2 removal into tree growth, etc., etc. So yeah.
Oh, so excellent. So you've brought up the concept of removal. So let's just let's set the table a little bit. So we're talking about mitigation, and we got at one end of the spectrum, and we got in some removal. So let's give some numbers just to help situate people in what we're talking about. So we've got mitigation. All the easiest in theory, technical, is in the oil and gas sector, replacing valves, for example, in the system that leak methane, or fixing leaks, mostly plumbing, essentially. That's mitigation. That is stopping an emission from happening. And then there's removal at the other end, Hinsby, that you're talking about, which is when you already have methane in the atmosphere, what are the tools we have to pull that methane out. And I'm going to add just a really important concept here, which is concentration. How much methane is there and how that can affect what we can do with it. And so there are higher concentration sources. I think Debbie, you were talking about livestock and manure and areas where it's the microbes doing their thing, the methanotrophs or the methanogens. Let me say that correctly. It's the gens, the ones that are generating the methane. The methanotrophs are the ones that eat the methane. But that microbial generation of methane at some of those sources is high enough that it can be captured and utilized. So I want to differentiate mitigation, stop it from being released, methane capture, which is useful if the methane concentration is, what is it, above 5% is where it's useful that it can actually, you can have combust it and you get the energy out in the way that we use natural gas. But below 5%, there's very limited, some of what you're getting at and what we talk about in the report. Hinsby, I want you to talk about what happens, what do we know and not know about how to deal with methane once you get below that 5%, which is what, something like 40,000, someone do the math, parts per million. I should know this from the report.
50,000 parts per million.
There you go. Thank you. And read the report.
Yes.
And so what is the actual atmospheric concentration? What are the methanotrophs that are on the trees? Like what's going on? What do we know about methane removal in this context?
Yes, and absolutely. I'm so enthusiastic and eager to get to that more difficult problem that I sometimes forget that, yes, we should talk about like higher concentrations, right? We do have technology, 50,000 and above, we have technology and we can get significant outputs out of this. But once the concentration is more diluted, the challenge of being able to access and every time more diluted pool of a gas that is very difficult to concentrate, right? It makes it more less effective, let's say, right? The challenge is higher. So as when methane is released, right, we'll start a process of mixing, and as we understand, the average concentration in the atmosphere is about 2.4 or 2 ppm, depending on which environment you are. It will vary, but let's say 2.4 right now, and 2.4 versus 50,000, right? Those are orders of magnitudes of a diluted substrate that now you are trying to interact with the goal. If the goal is to remove it to make an difference in the short term heat trapping capacity in our atmosphere, now we have a challenge of a very diffuse, all over the place, but low concentration, and now how you solve that, right? And as Gabby, you mentioned, check the study, but there are actually several categories that the group has analyzed, right? And each of those have addressed that challenge, the challenge of a very diluted pool, the challenge of what would you need to access that pool, the challenge of how can you scale up that pool, and the challenge of like what could be the unintended consequences of attempting either of those paths, right? And do we have enough information for that? So I want to focus on the atmospheric removal using ecosystem services, right? So when you think on that way, now you have a challenge of 2 ppm. You can be on the top of the soil, you can be on the top of a tree, you can be in the wet wall of a cave, for instance, okay? And this concentration is too low to grow happily, to make biomass, which is what microbes want to do, which is what they usually do, right? It is, you could use it as a substrate, but it's not high enough to really power you up, to really energize you to make biomass. So the microbes have that challenge, which is there, but it's low. Some microbes have been living with that challenge, and we have documented that before. There are soils, upland soils that have significant levels of methanotrophic populations, and we've known of them for a while. And yes, you measure atmospheric concentration and you see how it starts dropping down. So then how do they do it? Right, then the question would be, if that's not enough energy, then how can you still consume that and still make biomass, still divide and grow and be happy? Well, there are different clues, there are different options to be followed, and each of those clues and options will change by the ecosystem that you are focusing on. Co-metabolism, syntrophy, being an accessory form of respiration, or for instance, opportunistic. Sometimes you have periods, and then going back to the desert example with rain, where plumes of methane or high methane in comparison to 2 ppm is generated. And if you're a methanotroph that has been like waiting in there and you have that high concentration, then you consume, increase biomass, and then wait until the next rain, next plume, or whichever else, right? But we don't have a high clarity on exactly what is the right mechanism for these different places. So for the ecosystem services, though, we know when we can measure that they do exist, that they do happen. We just don't have yet enough knowledge to understand how we can maximize it, how we can favor it, how we can harness the power of nature, ideally in large surface areas, so then we can truly make a difference in the current goal to remove this diluted pool. Yeah.
All right, so we're gonna move to.
Gabby, can I just say one other thing? Because I didn't really differentiate it. So in all of these sectors, especially oil and gas, you have what I would call routine emissions. They're the things that just generally happen just in the course of an engineered system. But what we're finding more and more, and the satellites have been amazing at helping us do this. Carbon Mapper is one of the point source satellites that's been spectacular in this regard, is finding super emission events. These are more likely the non-routine events that can happen, and they couldn't put out huge 100 kilogram an hour, thousands of kilogram an hour. And the problem is that it's very hard if it's geopolitically, if this might be because of a war in Ukraine, it's hard to always stop these, but you don't want them to persist. And so you really want to have eyes in the sky that can make the invisible visible and stop this. And there might even be a way, as Hinsby was talking, I was thinking there might even be a way someday, because there's such large concentration events, to actually deal with that. If they're not lit on fire, sometimes these turn into fires and explosions, which make them even harder to deal with. But many times this is just sheer gas that's just pouring into the atmosphere.
And actually, that's a great transition. So I do want to talk about next steps in the future. But one of the things that you touched on a little bit in your introduction that I do want to come back to about, there's the climate impacts of the methane, but it's not just the climate. What else? It's methane is coming out of these leaks, but it's not just methane, and methane itself is a precursor for ozone smog. What else is coming out with this gas?
Yeah, so remember, the gas is underground. Depending on the geology underground, it's picking up lots of things. There's hydrogen sulfide, which in very small concentrations is deadly in a lot of this gas. You just it anesthetizes your nose, you can't smell it. And this has been a very big safety problem in the oil and gas and the coal mine sector for a very long time. But there are loads of carcinogens that go along with it, toluene, xylene. You get these different carcinogens that get picked up with it as well, and any array of volatile organics. And that's a big, big part of the smog problem. So there are issues, we call it gas or even natural gas. We associate it with methane because in many cases, that's the largest. In pipeline gas coming to our homes, it's like 98% methane. So if you get a leak there, you know pretty much what's in the pipeline. But if you get a leak at the field, it can be 60% methane and 40% other stuff. And we don't have good information around the world of the composition of gas as it's produced and in these gathering lines before they become processed gas, which is when we have a much better sense of what we've turned them into. And that is a very big unknown. When there's a leak, you really don't always know what's leaking.
Yeah, and I think I was hearing also benzene, which is a known carcinogen, being one of those, and actually even into the distribution lines into our cities and homes, that this is something that just is important to be aware of. All right, so I think we've laid out a good picture of the current situation. Let's talk a little bit about the future, and where we go from here. And Hinsby, I'm going to go back to you to maybe lay out a little bit more. You talked about some of the ecosystems, but for you, the atmospheric methane removal technologies, do they exist?
Yes, excellent question. So they do, they're promising. There are components that need to be worked and tested, right? For instance, bioreactor, and we have a lot of colleagues that are working on bioreactors, right? There are like a process of gas exchange limitations, energy investment limitations, etc. But they are people actively trying to solve those. And at higher concentrations, the technology with bioreactors is well established, right? Biotransformations, high value products, etc. And the idea is that they are now driving it to the lower concentrations with new materials, new catalysts, for instance, and trying to get into a reasonable output, reasonable speed, reasonable rates of removal, right? There is also a chemical processes like the photocatalyst approaches, where you can use different lights and you can destroy directly methane, or you can make it react with cover substances, etc. And there is also the maybe perhaps in an earlier stage with more unknowns, the manipulation of atmospheric chemistry, right? And that one, atmospheric chemistry is a beautiful, complex system that there is so little information and hard to constrain. So then, like, I'm trying to understand not just the different reactions, the different movements, dynamics, priorities, etc. So they are in different stages of development with different unknowns. But we do have these broad categories to which I invite our audience to actually check those details as we have listed in the report, right? To especially understand where is the biggest knowledge improvement that we need, but we need it now. Like these technologies, all the four of them have a reasonable propositions with variable levels of understanding, right? But if we were to make all of them function, we will have a shot to truly make that difference, to truly remove the enough level of methane to gain, some time in the next decades to deal with the CO2, which is the constant problem, right? So the methane is our quicker and speedier path to do again in time towards the solutions that we all are looking, not just in the methane space, in the CO2 space, or also in the nitrous oxide space, which I very much agree with Debbie when she mentioned there is nitrous oxide, and that's a problem. And I'll tell Debbie that that's also a problem coming from natural environments in large amounts and areas, right? So yes, these different categories are all progressing in different stages, but we do need the immediate action of the scientific community, of practitioners community as well through all of this process. And perhaps I almost did not emphasize one final component, and then I'll move Gabby, which is when we think about these solutions to remove methane, they all tend to be at large scale, large areas, large materials, types of processes. Well, it will have a connection, an interaction, a consequence to the communities, to the people living in the areas, policymakers, etc. So as we develop these technologies, we must do it in an integrated fashion with the social, economical, safety component that all of these technologies require. Yeah.
Thanks, Hinsby. This is actually a really important concept of this idea of responsible research and how, really being intentional, especially when we're talking potentially about modifying some systems like the atmosphere, which we are doing unintentionally. But this is where there's a lot. This is not just a computer program where you can tweak some knobs. And so I think before we go to audience questions, just a wrap-up question for each of you. Debbie, what do you see as the biggest opportunity in addressing methane in the coming years?
Well, I mean, in order to answer that, I think that I have to first say that the biggest concern I have right now that leads to the biggest opportunity is that climate change itself is starting to drive energy demand in massive ways. And that energy demand, thankfully, is somewhat being met by renewables, but a lot of it, when you package in artificial intelligence and data centers and everything else, is natural gas. Like, we're going to be potentially using hugely more gas in our future, which then means that, my biggest takeaway is that dealing with the leakage of this gas and keeping it in a pipe becomes the biggest opportunity out there. I mean, it has always mattered, but it is only going to matter more in the years ahead.
Thanks, Hinsby.
I think it's very hard to rank because we need to do this multi-approach. However, if I were to pick, I say we have the agricultural land management that will not require terrible changes to enhance this capacity to remove methane. And the other one is like the forestry space, because we are actively engaged in significant investment in reforesting, in managing land, in taking out resources from the forest, right? So those are very accessible. Activities are happening and adding the value, the proposition value of methane removal. It's very within our reach to make a significant number difference in terms of like the area and process.
All right, and so we're going to go now to the audience Q&A section. So just a reminder to the audience to please add questions to the Slido. And we'll try to get to as many as we can here. I think just to get one of the distinctions I kind of want to get at that's between the mitigation and removal side. When we talk about atmospheric methane removal, one of the distinctions we make is that atmospheric piece we're talking about already in the atmosphere, 2 ppm, very low concentration. But we touched on briefly some of these other sources that are a higher concentration. And so with your work in landfills, can you talk a little bit about what are the options for reducing emissions or capturing emissions from some of these agriculture or landfill sources?
Absolutely, and I think Debbie also has strong connections to some of the industrial practices because so the landfill is this big pile of decomposing material that it is actually engineered. In many cases, now you have these engineered landfills where you can control processes, like you not only now let it rot, no, you can have different layers of extraction, of pumping air, or removing or adding solutions, etc. So you can think of this for the landfills that I've been looking at. You can think of this in two ways: operations, right? Leakage, different active or not active waste, and then the next one is the long-term management. And in the long-term management, you could either promote methane removal, limit the emissions. You can promote limit the emissions, or you can do removal as well. So think about after closure of the landfill, you put a cover, and the cover you can manage the type of vegetation, the type of surface, mounding or not mounding that you can have with that, and that will make a difference for trapping what is coming from the bottom, so carbon emissions, or can make a difference from what is surrounding, which is also removing methane, right? So that's once the landfill is closed, the long-term post-closure, and then in the operations, you can actually have a system in which I think there is a practice now where you reduce organic matter input, right? So you do that reduction.
Composting.
Exactly. Composting, and it's perfect. It helps everyone. We should all do composting, for instance. But even at a higher industrial level, some landfills are starting to do some level of reduction of organic entry, right? But after that happens, you could also manipulate, by the way, the level of water just by recirculating water in the landfill, and you could potentially alter the electron availability, which links to the metabolic activity of producing or not producing methane, right? Or
but does that make more N2O?
That will be the challenge. Then you have to play this. How much strength do I put into repressing this system, and what happened with the other output? And if you find the right spot where you limit both of them, then you could. So there is significant bottle level, lab level testing, and they all meet the challenge of, can you run this at a whole landfill level, and that is scaling up, right? So for instance, we've been playing with some manipulation of metals, which will lead to either enhance the pool for methanogenesis, but in a way that is connected to high and effective removal, right? So you actually turn that into a opportunity to make a benefit, to increase the methane, so it's higher concentration, so you can transform it. Or you can just go all the way around, which is like just limit the pH, and methanogenesis will be very heavily challenged, and N2O production will also be challenged by a low pH. What can you use that is an innocuous way to lower the pH? That is where the details start, coming to be. Okay, let's keep figuring out these particular components that are viable and not too expensive, and so on. Yeah.
So microbiologists, biochemists, there is work for you out there. Lots of fun stuff.
Along with the engineers.
Exactly. Debbie, did you want to weigh in on that? Or I've also questions for you on measurement.
Yeah, just a couple of thoughts on the landfill. So Carbon Mapper, in collaboration with the satellites, they're also seeing a lot of super emitting landfills. I think that was a little bit of a surprise, how much methane can leak from a landfill, but it also helps in being able to differentiate the landfills. Which ones are failing, and are they systematically failing? And is it just a one-off failure, or is this a constant failure? So it can help actual experimentation, I think, in that space. And then the only other thing is the feedback mechanism of food waste, which is really the food waste that creates the methane. And so the idea of, and that feeds into agriculture, and the methane that comes from agriculture, just trying to true up these systems as the world's population grows is just a good thing. It starts to become virtuous if you do it right.
Nice. I like it. And I'm going to pick up on that. You mentioned what Carbon Mapper is seeing. And of course, there's now an array of additional satellites and observing platforms. I think MethaneSat also launched last year. And we've got a few, I think the EMIT instrument on the space station. I was wondering if you could, I think there's a great RMA graphic on this that came out recently. If you could talk a little bit more about the technology, the cost, and the implications for moving from, all right, there's data, that's an observation, all the way to action and accountability.
Yeah. The very first thing becomes affording to collect the data. And I think this is true for the nonprofit satellites, especially with Carbon Mapper and EDF's MethaneSat, because it's a costly endeavor. Not just to launch a satellite, build instruments and launch a satellite, but to then take the data, manage the data, and turn it into something. So I think that procurement of data and leads to the usefulness of that data, which is incredibly helpful. And then the data finds its way into decision making in very odd ways, sometimes because companies and countries are very competitive. That's helpful. Who wants to be the best? Who doesn't want to be the worst? That is very helpful. And then into the economy when it comes to pricing. Had the waste emission charge that EPA put forth for methane been implemented and the super emitter program been implemented, you could see that you would finally get a carbon tax out there, which would be on methane, and you could use this data to do that. And then the third way is that, especially in the oil and gas space, these are markets. Buyers have certain purview over the market to say, I don't want to buy high leakage gas. I want to buy low leakage gas. And so it starts to change the way the trade is done in the world. And China's starting to lean into a lot of this to be, cleaner and better than much of the world, especially in renewables deployment, but then also in how they manage and purchase different resources. So I think that this data finds its way into so many aspects of policymaking, of economics, of the way trade is done, and mostly because once you can see it, you can't really deny it.
Yes, I think there's work that needs to be done to convert that. And I think that there is actually, the International Methane Emissions Observatory and I think the value of some of these approaches that you're talking about, like the European Methane Performance Standard, just internalize the cost, right? Like that any good economist for these things makes a lot of sense. I do want to pick up on something that is a question from the audience. And Hinsby, go to you on this question, which is around tradeoffs and how is the potential and scale for atmospheric methane removal, how does that relate to other anthropogenic emissions? And is there a risk of unintentionally prolonging emissions from oil and gas sector, for example, or other anthropogenic sources, or encouraging, one of the risks, shift towards more intensive agriculture, where you have the potential to concentrate some of the gases? How do you think about those kinds of interactions?
Yeah, that's an excellent and hard question, right? Because on one end, we do want to contribute to the solution of removing methane, earning more time, being able to improve conditions or avoid the conditions getting worse. And on the other end, we do want significant change. Right? We do not want the sources that made us wanted to start removing the methane and that made us have to start removing methane. We don't want them to continue. We don't want to also intensify some of those practices at all, right? So the rationale will be as this is, if you were not to take action now, in both fronts, not just one, not just removing, right? We will overpass the capacity and that to hold or to handle the current changes, which I think we have very limited capacity, by the way. And so that's along with the removal progression, the progress in removing, we do need to work just as hard, or sometimes even harder, on cutting the sources, on managing the sources better with the current tools, current technology, and all of that. So we'll need to tackle both of them.
Yes, thank you. I think this is one of those kind of scale time issues and trade-offs. And I think, Debbie, you were talking about, it seems like future projections tend to agree about demand for oil plateauing, but those projections actually range a lot more in terms of natural gas future demand, and in a world where we need to manage actively all sorts of things, moving water, cooling and heating, spaces, all of those things. Speaking of, one of the solutions that for shifting away from fossil fuel, especially in industry, but also in electricity generation, or at least usage, is hydrogen. And Debbie, I was wondering if you have had any thoughts about, currently most hydrogen is produced through natural gas steam reforming. What are those interactions, and is this something that you've thought about?
Yeah, and I have colleagues that work a lot on green hydrogen, which is produced from water. But there are many shades of hydrogen. And like you said, I don't know what we call it, black hydrogen, the hydrogen produced from methane itself, from gas, where or gray hydrogen, where it's a double whammy, because not only do you need to get the methane, the gas, which can leak along the way of the supply chain for making that hydrogen, but you have to blast it with steam, and you make the steam with gas. You heat up the water with gas. And so it's really an amplifier, and it's from the 1930s. That technology was used a lot in oil refining. That's where it evolved from, because they used a lot of hydrogen in oil refining, and they had wasted gas. So they would blast steam at it and create the hydrogen. So, we're now nearing 100 years of very old technology. And I think that there are real questions of how we would want to deal with, and get hydrogen and go more into, there's a blue hydrogen space, which is a blend of gas, of natural gas and hydrogen, and how you re-inject and you carbon, you capture the carbon and sequester the CO2 that comes out of the steam reform methane, and you get your hydrogen that way. But two things come to mind with hydrogen. One is the systems can't leak. Hydrogen is even more explosive. So we need to clean up our gas systems, for natural gas now, for the methane, if we're going to do hydrogen big time anyway. So we might as well get ahead of that. And then another one just to be mindful of is that though it's weaker, hydrogen is also a greenhouse gas. So we just don't want to leak. It kind of comes down to that wherever we go.
Yeah, and Hinsby, you touched on one of the technologies approaches for atmospheric methane removal is to enhance the atmosphere's capacity to oxidize and remove methane. And to Debbie's point about leaking hydrogen, one of the things I think we touch on in the report is that competition for that oxidative capacity. And just I was wondering if you could talk a little bit more about removal technologies. We talked about, are they ready? Are there any that are shovel ready in your mind?
Yes. So I'll address this question in two ways, right? Like, first is that I very much agree with the avoiding leaks and working extremely hard at avoiding leaks for the hydrogen technology, because as the book also reflects, as the report reflects, it will compete with one of the largest natural sinks of methane in the atmosphere. It will take the same reactant, right? And by reacting and removing the availability of that reactant, now the methane will have a longer lifespan and continue with this higher warming, very nice grabbing blanket, right? So we have to be very, very careful on that, and because there is, at least as far as we understood and analyzed, we do not have a good shovel-ready technology to mediate that type of reaction, ameliorate that type of reaction, etc. Right? So it will be one more challenge to the removal of methane, even under the natural dynamics. Now, of all the different technologies, perhaps the ones that are closer, right, are the ecosystem services type, in the sense that they will have a potentially a lower number of unknowns with risk to it, that also have a significant large areas to work, that have in different levels active efforts that perhaps were not focused on methane, but that can be expandable to include methane. But I do want to touch on one combination of these, reducing emissions plus improving removal, enhancing removal, right? So for instance, yes, I have significant experience with engineered landfills, and they're like marvels of technology as well. But there is in many places landfills that have a more basic structure, that do not have linings necessarily, that are not highly complex with technology, etc., because there is a broad global population, right, with the needs to manage the waste. So, and how do we, in those places, for instance, reduce our emissions? So my proposal is something that can access known technology, as we discussed, right? Organic matter is the source of your methane, and composting is something that we understand well, very effective, and all of that. But how do you demonstrate to, let's say, a local community somewhere in the tropics where I work a lot? How do you demonstrate to them, like, this is beneficial, financially better, and environmentally like an outstanding approach? So if you can establish a accessible monitoring point where you can literally see the methane, and we do this when we try to talk to local authorities, like we can show you the methane fluctuating from very little and to a huge plume of thousands of ppm, right? And you could demonstrate not in a long-term period, you could demonstrate that if you start excluding the organic matter in that active phase of the landfill, your emissions reduce quite a bit. But not only that is what you can demonstrate. You can also demonstrate that with the composting and the materials generated by the composting, you engage that into your reforestation efforts, and now you have more vigorous trees that also can remove the methane that you avoided, that you were not able to avoid to emit, right? So not only you reduce emissions, but you also start capturing whatever was emitted either by your landfill or by surrounding other activities, other areas. So I think that's very demonstrable. You can work with local authorities in different parts of the world, etc. We just need the determination and the programs to be able to start doing this to address these different forms in which emission avoidance and removal can also work together and benefit each other.
Nice. Debbie, do you have anything to chime in on that one? Or I was going to pick up on the lifetime question, which I think is actually one that comes up a lot with methane that we didn't actually dive into at the beginning. But one of the key concepts around how we think about methane, and that I think a lot of people get stuck on, is the idea that methane is relatively short-lived compared to carbon dioxide. So once carbon dioxide is put in the atmosphere, it sticks around for you might cycle between the ocean and the atmosphere and the surface ocean and the biosphere quickly, but generally that CO2 is gonna be there for centuries to millennia. Whereas methane is reactive and has an effective lifetime on the order of 10 years. How do you, Debbie, when you're talking to people and trying to get them to think about why methane won't solve itself, it's going to go away in 10 years. What is this an argument that you've heard, and how do you respond to that?
You know, it's interesting. I almost feel like we're in round 2 on climate action here. You know, we started 30 years ago on CO2, and maybe we're just progressing as long as CO2 lives. It seems like the conversation just keeps going and going, and the progress has been maybe slower, I would argue, than it could have been. I don't know if we've learned from that or if there's more evidence of climate change around us, and the disasters that are happening pretty much, you know, all the time. It's becoming more observable for the human eye, for people, and for, you know, local communities and disaster relief, et cetera. I feel like there's been a lot less pushback on methane and mitigating methane and having this conversation on methane removal than there had been on CO2 for mitigation and removal. I feel like that was a very long conversation that must continue, and hopefully will really bear the fruit. But methane has struck a chord in a good way, I think. It's really struck a chord. Maybe it's because it's partly a commodity. It's recognized as natural gas, maybe because we now have satellites, maybe because we've experienced what we went through with CO2, maybe it's because we're seeing more disasters. It's seen as, and maybe because it's short-lived, you know, get on it. Like there's no waiting. This is as immediate as it, you know, reacts very powerfully. You need to stop it very quickly. So I feel like there's way more to do, but I feel like the attention from parties, all different stakeholders, is there, which is why we're having this conversation.
Yeah. Hinsby, do you want to weigh in on that?
I actually got distracted thinking about agriculture, right? Thinking about how agriculture, it's something we've been doing for a long time, and release methane, and the methane may last a long time or not, but you know, in which other ways we can use agriculture to reduce the life of methane, and long-term practices like tillage, no tillage in agriculture, or water management, or even the type of crops combinations, all of that is something that we've been doing for a while, for significant times, right? But the direct connection of that to methane lifespan, we have not done that. So I've lately been very, very attractive, very wanting to test and learning from my colleagues, especially the implications that the different practices that agriculture have. And I'll give you a simple example on that, and reducing the lifetime of methane through removal, right? I live in Phoenix, Arizona, where water is very important, and water management in an area where you have two crops or two harvests in a year. It's a very actively agriculture area, right? There are recent studies, recent evidence where when you manage the water and actually reduce the whole consumption of it, so you save water in the West, you get similar crop yields with a significant reduction and added consumption of methane, right? So
Consumption of methane from those natural methanotropes.
The natural methanotropes that are in the soil. However, we do have to remember then we can add the next complexity, which is, well, which type of crops and which type of crop management, right? Because it's also having demonstrated that as you do land transformation into agriculture, the natural methanotropes start dropping down, right? You drop the numbers, and that has to deal with the type of metabolisms, addition of fertilizers, et cetera, that displace them out of their energetic growth space, right? So then the next question is like, okay, so not only it's a matter of managing water, but it's now a matter of managing the geochemistry of agriculture. How do you do that, right? And there are, for instance, like mineral additions, mineral surfaces that will enhance, have been shown in a small scale to enhance the activity of these methanotropes to help perhaps the recovery in the advantage or disadvantage that they lost when the agricultural system came in, right? So tillage and no tillage has a significant effect on CO2, and that has been shown through different research. Tillage and no tillage would have a connection as well to how more or less challenged are methanotropes in these environments, but it wouldn't be enough, it wouldn't be sufficient to just change between different regimes. It will be now a multi drivers process to help us do both, again, like they reduce emissions, avoid emissions, and at the same time create the conditions that in the other periods they are removing as well. So yes, I'm too excited about that type of like potential area that agriculture moves, and how we need to be putting more efforts on that. But I'm certain that it does affect in some level the lifespan of methane in the atmosphere.
Excellent. And so I think we are coming close to it. So I want to give you each a time to give some last thoughts. I think Debbie went on that lifespan, and you talked about the blankets before, and I think I used the blowtorch example. Some of the examples that I'm hearing is actually the short lifetime is a benefit in terms of the speed at which, if we reduce emissions, if we actually can see a reduction in concentration, we actually can get that climate benefit quickly. And a lot of people don't realize that methane is actually contributing about 0.5 degree Celsius to current warming. So even though it's 200 times by volume less concentration in the atmosphere, because it's so potent, even though it's short-lived and because we keep emitting it, it actually is a very significant source of warming today, but also potentially, I think, Hinsby, you're talking about kind of a throttle or an emergency brake option as we work on the marathon of the energy system transitions to reduce CO2. And so basically, as a prompt, I want to give you each, starting with you, Debbie, just a last minute. What are the key things that you want the audience to take away from our conversation today?
Well, first, thank you so much, Gabby, and to the National Academy for even doing this. And the fact that there are about 1,000 people signed up to listen to this really does give me hope that there's so much interest in the varied questions. Like, there's interest in every aspect of methane's mitigation and removal from all different sectors, because I think it's that broad awareness for something that's invisible and odorless and is largely a waste product. It's it's really heartening to know that there are so many people thinking about this. And I am very encouraged by the upcoming COP in Brazil. I think there's going to be a lot of discussion on methane there. And every Climate Action Week, I'm getting ready to go to London Climate Action Week. There are so many panels on methane. I'm just, I'm heartened by the awareness and the action out there. But thank you for hosting this.
That's great. Hinsby.
Oh, same. It's such a pleasure and so exciting to have so many people interested on methane, to have the national academies provide this avenue to enhance this discussion. I would say that methane has been biologically produced since the beginning of life on Earth, really early records, right? Methane has been a process that microbes have mastered long before we started any industrial modifications of our atmosphere. And thus, the natural capacity to flux in a dynamic way, this pool has existed. But due to our activities imbalance, our excess, right, we have now pushed it to a ways in which we need to go back to nature and pick a lot of its potential, a lot of its capacities, but we need to support that. We cannot continue emitting first. We need to work with as many alternatives as possible, provide the information that is needed to evaluate how do we reduce emission, which is, where we need to be doing, along with our emergency brake, along with let's gain time with the capacity, using the capacity of our technology or our ecosystems or our practices to also enhance that leverage that we can on this very dynamic, faster termed type of gas. So I'm very excited, and I do make a call of action to all our audience today to either interact with your local stakeholders, policymakers, scientists, or industrial partners to take the available opportunities that there are around this subject, around this discussion. So I'm super excited to hear all the panels, all the discussions in the next large or global meetings, for instance. So thank you for the opportunity as well.
Thanks, Hinsby, and thank you to the National Academies for giving us a chance to talk about reducing and removing methane emissions. I think we've learned a lot about the different sources and some really exciting removal, and just again, all praise to the methanotrophs and microbes and all the amazing nature and ecosystems. And but with the recognition that we are not going to be able to remove our way out of the problem alone, that we need to also be putting in place some of these really available mitigation strategies, from fixing leaks to composting, to address this super pollutant of methane. And back to you.
Fantastic. Thank you so much, Gabrielle, for moderating today's informative conversation and all your work in this space. Deborah and Hinsby, thank you also for sharing your incredible insights. To everyone who joined us today, thank you again for your interest and excellent questions. We did receive a few questions about hydrogen, so I want to plug our climate conversation from last June on this topic. For our viewers, we review all your feedback, so please take time to take the survey linked below and let us know your thoughts on today's programming. This conversation was recorded and will be available to view on the same page immediately after we end. So the Climate Conversation series will be taking a break in July, but please come back in August for our next climate conversation on educational pathways for a climate-ready workforce. Keep an eye out for the registration in the climate newsletter. Thanks again to my colleague Brent Hurd on the Board on Energy and Environmental Systems, and as always, a big thanks to all my National Academies colleagues and staff who supported today's event behind the scenes. Take care, and we'll see everyone in August.